Do you guys have some too? Okay, well.
You can take it.
Alright, I had a hard time writing problem 1-3 nicely, the proof for that.
Cardinality of A is less than B and C is less than A. So you have an injective map from A to B, right?
Yes.
But you have an injective map from A to C.
Yes.
C to A.
Right.
So you get an injective map from C to B.
Right.
And that means the cardinality is less.
Yep.
Okay.
And doesn't it have to be not surjective too?
Yeah, that's if it's bijective, it's the same, right? Cardinality.
Oh, there is some. When did they? How old is that?
Oh, I don't know how old it is. Do you guys remember this one? You guys know how old this is?
Yeah, I remember that one.
I can't remember. There's only 3.
So the cardinality of A is smaller or equal to the cardinality of B. Yes.
That's.
And the cardinality of C is strictly less than the cardinality of A. This implies the cardinality of C is strictly less than cardinality. So 1 is the cardinality of C is smaller or equal to the cardinality of C, right? So this one means we have phi from A to B, this is injected. And this means we have psi from C to A, that's injected. So we have first psi, then phi is injected from C.
Okay, alright.
So that gives you this one.
And that's just based on the rule that the composition of injective is injective. Okay.
So the second thing was we have no injection. A to C. Let's call it alpha. Right? If you want strict inequality. And we would like to show that we do not have this injection from right. So if the cardinality of C is looks like I don't know how I can that we have no injection from B to C. We have so no injection like this. because of the strict inequality here. And we do have injection this way. And this one was the assumption. No, this one is our claim. And this one is the assumption, right?
Mm-hmm.
So if we had an injection here, the composition would be an injection. So we have an injection here, right?
And is that contradiction?
And that's a contradiction.
All right. Thank you.
Is that it? You
I
have
guess
more?
that's it.
Well,
We're alternating.
here that book, chapter 0, was, I don't think, very smooth in the sense of strict inequalities. And so that shows up. I mean, I'm perfectly willing to work with inequalities for cardinality, but I didn't care much about strict inequalities. But it filters in there from the book.
All right. So we're most likely going to see lessening equals to our gradient. Okay.
And I haven't even thought about your exam. I was making my 244 exam.
You can-
Oh, so no exam.
Right now. This moment.
You look so disappointed right there. You wimp. That's what he's thinking in his head, yeah?
Are we
I don't
considering
think the final is going to make a huge
Difference.
in terms of grades.
Mhm.
Yeah.
I think you will kind of perform the same way you did in the past.
So lousy.
No, the exams weren't so bad.
I still haven't looked at mine, you know. I refuse. I know mine's is in the gutter then.
So, justifying each step.
Hey, should I go Google like Google like the most obscure math problem?
Oh, that'd be so cool. Yeah.
Analytic solution finds overlay.
Oh, okay. It's like shucks, it's everywhere.
It has inverse.
Right, so cancellation meant that so R satisfies multiplicative cancellation if for all z not equal to 0 and for all a, b in R. A, C equal to B, C implies A, B, right? Okay. And so if we have, what was the exact formulation?
contradicts your operation. You just say they're community and they're relation.
So just design each step that the cancellation holds if and only if there's no zero divisors. Okay. So zero divisor. Z is the zero divisor. If xz equal to 0 for some x is not 0.
Are x and z real numbers? What are x and z? Are they real numbers?
Elements in the ring, elements of R.
Okay.
So R is just some algebraic structure.
Okay.
So you have axioms for algebra, associative, commutative, additive inverses, distributive.
So a ring was closed on addition, closed on product, and then it was there was no multiplicative inverse.
It's not required.
Oh, it's not required. So it cannot show.
It can happen.
Okay.
So cancel it. Let's say no. So let's say cancellation implies no zero divisors. And then you can say zero divisor implies no cancellation. So here you take A not equal to 0 with A Z equal to 0. This implies A Z equal to 0 times Z. But A not equal to 0. Okay, so that means no cancellation. So now we would like to show no zero divisors. Implies cancellation. So you would say that for cancellation we have A Z equal to Z, and we would like to show that A is equal to B. This implies that A minus BC equal to 0, which requires a few algebraic steps, but so that means you can bring this to the other side with minus. distributed load to factor out your C. But that's what we are allowed to do in the algebra, right? Now we assume no zero divisors. This implies A minus B 0. And this implies A. Okay, it's kind of a routine exercise using axioms in algebra.
So that original, the cancellation implies no zero divisor as the claim, right?
The claim is the two are equivalent. Okay. So the exercise there, so the problem was cancellation if and only if no zero divisors.
Okay, I see.
Okay, so this one here is this direction. This one.
Okay, so anything.
Yes.
I have one. I think this one's a little, not too hard, but I think I just want to make sure I could write it out cleanly. So I disproved this one using countersample, and the assumption I added was injectivity. And I have to prove that.
Okay. Sounds fine. You want to write it out?
Yeah, sure.
Sorry, falling asleep.
When he politely reminded you.
Huh?
Oh yeah. I woke you up for you.
You gotta get some new pants, man.
Oh, these are old. These are since high school.
So what is that? Yesterday.
5 years ago.
Yeah, high school days on that one.
I think I'm the oldest one here, since Valerie's not here, or Tosh. You can call me Daddy.
X to U. No, Y. U is a subset of that make sense?
I thought they were going to prove something.
I thought I did prove it.
How about that first line? Isn't that already everything?
What? Wait, what?
And I don't understand. That line is a and A is an X. Where do we ever use that A?
Oh, I don't know, I was just defining it.
For what?
Oh, I guess I didn't use it. Oh, I thought you did. Yeah, I thought I used it somewhere.
What were you smoking when you did
I
that?
don't know, I was tired.
You know what? That's probably
Okay,
farther than I would have.
so-
So
Back to the drawing board.
Okay.
get up there.
Two sets are the same. And then don't bother.
What's that?
Just leave it there.
Okay,
You can
right.
erase the other backboard.
Alright.
Two sets are the same if each is a subset of the other. Okay. So let's start out. No, later. Two.
Okay.
Say y little y element in f of x minus u.
Okay.
Okay, so we assume it's an element in the set on the left, and we try to show it's an element in the set on the right. That means if and only if f of y belongs to x minus u. So this
F of y.
implies not equivalent, right?
F of capital Y?
Where does
No,
that
no.
take you? The
Okay.
F of y.
Hmm?
Where does F of y take you? Like, doesn't F go from x to y?
Yeah, it's a map, so you apply it to the element, sorry. No, sorry. Erase what was on the right.
On the right.
Yeah. That one. Okay. Y belongs to f of x comma u, so y is equal to f of x for x in x, capital X minus u, right?
So can I say y equals f of x for x is a member of x, but x is not a member of u?
If you take x minus u, wouldn't it have to be?
So now you would like to, so don't put an implied there. Injectivity implies
Injectivity over the implied sign?
injectivity of f implies
Can I just notate it like that?
no, implies. Spell
Okay.
out the word. That y not equal f of a for a in u. right? I mean, this y is the image of an element in x minus u.
Yeah.
It cannot be at the same time the image of an element coming from u, because then you would have two different elements mapping to the same y, right?
Okay.
So, f of x is an element in y minus f of u. Of capital U.
Yeah. Would you use the regular F notation there, or would you use your bar notation because you're going to run it on the whole set?
At some point we gave up on the bar. We said for a while pedagogically this was relevant, but eventually we get rid. Okay, so it doesn't come from A. So we can remove f of u because y is not in f of u, right? So that's one direction, right?
Yeah.
And if you say, let's do the other direction. So let's say y belongs to y of minus f of u capital U, right?
Yep.
This implies
Biconditional or?
yeah, no, that is fine.
Okay.
Y is f of x. And y is not f of a for a in u.
Yeah.
Y is not.
No.
Right?
So equal?
Not equal.
So sorry, it's not
F
what?
of A.
F of a.
No, leave that. Y is not equal to F of A. Where A is
For
in.
a in capital U. And maybe for the first part we should have written y equal to f of x for x in capital X, right? And that means that y is f of x for x in x minus u, right?
Yeah.
Sorry, what's that one more time?
Y equal f of x for x in x minus u.
Okay, alright. Which implies,
Isn't that it?
yeah, thanks.
Oh, where's your box?
And to make it clean, before the first part of the proof, you can make subset in quotation marks. And for the second part, you put superset, set,
Superset?
other way around. Subset, but the other way
Oh,
around.
okay.
Yeah.
Alright. Cool, thanks.
Oh, that goes back to you showing that for two sets to be equal, they got to be subsets of one another.
Right.
Yeah.
Got it. Question.
Avoid eye contact.
Oh, me too then. Okay. What are we looking at?
My foot.
Yeah, for me.
Two.
I told you what to do.
Identify the equivalence class with the points.
Let me ask.
Are those questions from his stuff online?
Consider the set of real numbers.
From the practice sets?
And the two elements are equivalent if they differ by an integer. Verify that this is an equivalence relation and describe the equivalence classes. Probably this is a good exercise for somebody taking 421. It might also be a good exercise for somebody taking complex variables or someone taking math 140.
Really?
No, yeah, really.
Or somebody who likes Euler.
What is that? These double signs.
Length.
Okay.
Oh, is that what the two bars around the thing means? Yeah, that is length,
It's
right?
like absolute value, but
No,
sometimes
but-
when you don't do it in the real numbers, you add.
There's a formula or whatever, right? It's a little more than just taking the absolute, just chopping off a sign.
Arc, is that arc?
No, in that case, when you
What is
do
that?
complex numbers, then
Square root of
is,
a squared plus
the-
b squared. Yeah.
But it's still the idea of length.
I
Yeah.
saw that on our exam with things.
Okay.
I accept my death.
The secret background, I mean, to this idea is you can define a map. Okay. Yeah, I would like to write, do you want to write? Kyle, go and write.
Alright.
Kyle Alvata just asked us to write, to go and write.
Write down the exponential function. The exponential function goes from the real numbers to the complex numbers, right?
Oh, Euler's identity, huh? Is that what you're gonna use? I hate that thing.
So
Come on, Kyle.
exp,
Is it e to the I theta equals?
exp,
Oh, there you go.
that's exponential function. Right.
Yeah.
From the real,
From,
colon,
oh, okay.
R to C.
Put a bar.
Put a bar into the C. Map. Yeah. And theta maps to, okay, put a vertical line at the left end of the arrow. To E to the 2 pi I theta. Okay. So, the claim is, theta is equivalent to theta prime. Now you can put the wiggle.
Theta prime.
If and only if exponential function of theta equal to exponential function of theta prime. You remember when we did equivalence relations, we said having an equivalence relation is the same as partitioning the set. So elements that have the same image belong to the same equivalence class.
Because they're from the same piece on the other side.
Yeah.
Partition.
So, and if you spell it, what does it mean that exponential function of theta is equal to exponential function of theta prime?
Theta equals theta prime?
No.
No. The difference between those two.
Okay. It means that theta and theta prime differ by an integer, right?
Some k.
Because it's, I mean, 2 pi variable.
Oh, so the phase might be different?
So the equivalence classes, you have a copy of Z sitting in the integers, but you can shift it wherever you want, right? So, the class maybe this is enough to write down if you remember all the background. So the statement here was, I mean, first of all, it's an equivalence relation, that was easy, right? And the second thing was identify the equivalence classes. So, 2 elements belong to the same class if they have the same image under the exponential function. And if you think in terms of the real line, the integers are one class, right? But then you can take the integers and add any number. It will still give you one class, right? So you get one class for every element between 0 and 1. Because afterwards you start with okay.
Afterwards, can you have a diagram?
A diagram
Diagram.
of what?
I don't know. Of what you were explaining.
It's not really circle and complex plane.
The
A
point
circle and a
was,
complex plane.
no, it's not so. What happens is you have a real line here. You have the circle here.
Okay.
And you wrap around, right? That's what this map is. Because this one here is cosine 2 pi theta
Plus. Minus
plus I times sine
2 pi theta.
pi theta. Right?
Yeah.
Or when I write it, when you think of this as C or the plane, then this one is the point cosine 2 pi theta sine 2 pi. So you take this line and you wrap it around. So 0 here goes to this point, and then you wrap it around. So the crosses are the integers, and they give you one class. Well, they form one of the equivalence classes, right? All of them are equivalent. But then, if you took this point here, this point, this point, this point, they differ by an integer, right? So this is another class. Or if you took this one, this one and so on, that gives you another class.
So there's infinite many classes?
Yeah. You get one class for every number between 0 and 1. Strict inequality at one end.
This is injected.
No.
Because the parentheses show that it is injected.
Oh, but
That was
the map from the equivalence classes to the circle is injected.
So we need to go here as well. Okay. That makes
Okay.
sense.
Yeah, that makes sense.
because
So
it's
that
wrapped around.
means each point of the circle gives you one equivalence class. Exactly.
So
Circle.
this notation is only duplicate plus.
That means the equivalence classes of real numbers.
Gonna die. I'd rather jump on a landmine,
That was beyond.
let alone.
Two
They have all in sessions, right?
Huh?
But they don't get the movie right away.
Wait, what?
Was that?
You should have set up that they can call in their questions.
Oh God.
Oh, you mean
Just use
Todd-
your cell phone, yeah.
Oh, we could. Yeah, we could. Because he's not teaching right now,
I
right?
told you, just, take your laptop, Google the most obscure math equation you could find or something like that, some ridiculous theorem.
This is easy.
I know, yeah. Make some assumptions, pop!
It's full of one of them already.
I don't feel like asking
Yeah.
questions now because they look-
Traveling salesman problem.
P versus NP.
Yeah.
What?
Equals NP.
No, it's like, I think like one's like a sub of like the other one. Right,
No,
one's
no.
bigger.
No.
Some millennium problem.
P
Talk about
as in
it a
P,
lot,
the power.
yeah.
P as in the power cell.
No,
Okay.
The quest, I mean,
I think it's like
you know the
non-polynomial.
traveling salesman problem.
Sorry, what was that?
You know the traveling salesman?
Oh no, I never heard of that. Maybe I did, but I just probably don't remember.
Okay, so you have a bunch of locations
Okay.
and you would like to visit each exactly once.
Okay.
No, you want to visit each once. You may not be able to do it with exactly once.
Okay.
So devise a strategy.
Brute force.
Now, if you have two cities, you can just go from one to the other and you're done, right?
Yeah.
If you have three cities, well, and maybe there is a road, maybe there is not. I mean, you can set up the road so that you have to go back to the other, to the city where you were, and that's fine. But the question is, how does the complexity of the problem grow as you have more cities?
You mean how many more possible ways is there to travel?
Right, I mean, you know the Königsberg Bridge problem?
No.
Is that the one where he has a like one spot to go
Okay,
to?
so you have cities,
Yeah.
and you would like to travel between the cities in such a way that you travel along each road exactly once.
Once, yeah.
And you can do that exactly if each city is connected by an even number of roads to the system. Or if there are exactly two towns that have an odd number and everybody else has an even number. Okay. I mean, the argument is simple. The argument is if you take a town and you want to travel along all the roads, you don't want to get stuck in that town. So if you have an even number, then whenever you come in, you can go out. If you have an odd number, it's still fine as long as this town is the starting point of your route or the end point. Okay. So if in this situation you have a town where to start and where to finish, if all have even, you can start anywhere you want and eventually you return. So, and it's easy to devise a path. What you do is you start one place, you travel until you get stuck. If you didn't cover something along the way, then you put in some side trip and it'll get you back to that point. And then you modify your path by including the side trip.
Sounds like an algorithm right there.
It's an algorithm.
Yeah.
It's a simple one. But for the traveling salesman problem, there is no algorithm. And if you look randomly, the number really goes up fast.
Like factorial kind of growth or something.
Yeah, probably. I mean, that's a primitive way. Factorial would say you just take every possibility, right?
Yeah, you're not pruning.
But the question is there a better algorithm where the complexity does not grow that fast? So where the growth in the problem is only polynomial.
Wow. That's what the P stands for, right?
A non-polynomial or non-polynomial?
You probably need to see a picture just to get the grasp of the problem.
Yeah, probably. I could kind of see for the second one though.
The King's
But
Bridge.
I
or whatever.
understand the
The second
factorial.
one is a math 100 problem.
Okay. The second one, okay.
Don't take him for Math 100.
No, that's called the Königsberg Bridge problem, right?
The King's Back Bridge, is that what that means?
Königsberg.
Who's König?
It's a town.
Oh.
Königsberg.
Oh.
Kaliningrad nowadays.
Is it in Germany?
It was. It's Eastern Russia, so it's Russia. But it's where Euler had a position for a while.
Is he the one that posed that puzzle, or he dabbled in that?
No, he is supposed to have gone for a walk on a Sunday afternoon and solved the problem. So the question there was, can you walk around town crossing each bridge
Oh yeah,
exactly once?
that's what they use. Yeah, bridges. I remember that. Yeah.
So, what's the map?
What's the map?
He wants you to make the map for him.
Design a city, you mean?
There's the bridges.
I'll say egg.
An embryo, yeah.
It's the river, right?
Yeah.
Yeah. I remember.
You've seen this before too, yeah?
Yeah.
I taught high school math. I would do this to my kids.
It's fun, yeah.
Yeah, it's kind of fun. Maybe they might solve the problem, the millennial problem for me.
Question is, are you gonna split the money, or
Yeah.
even though they solved it for you?
50.
Probably I need one more bridge here.
Uh-oh.
Right, I mean, here I have 3, here I have 3, here I have 3, and here I have 5 right now. Okay, so
What's the objective here?
you can say this is one part of town, this is one, this is one.
One side, yeah.
And now
You know that part is just that. Oh no, it's not.
each of them is connected with an odd number, and I have 4 of them, so that one doesn't work. I'm sure if you take your cell phone and type in Königsberg, which problem, it will give you the correct map.
You forgot the most important part though.
What?
The name of the town.
Königsberg. You just have to learn how to pronounce it correctly, like Euler.
König? Isn't that King?
Königsberg.
Isn't that how you say king or something like that?
Yeah.
My
König
boss's last name is König, yeah.
Yeah, it's King's Mountain.
King's Mountain.
Yeah.
So how do you say mountain in German?
Yeah.
Berg?
B-E-R-G.
Doberman Berg? It's the Doberman Mountain right
No,
there.
my name is actually not German.
What?
What?
I gotta leave. This imposter sitting here.
It's Dutch.
Dutch.
And it's probably even more English than Dutch.
Doberman is.
You know the White Cliffs of Dover, right? Have you ever heard of the White Cliffs of Dover?
What is that?
You know Dover.
Ben Dover.
City in southern England. And you can, that's the nearest point along the channel between, so Dover and Calais is that one ferry.
Is that the English channel?
Right, the
Okay.
English channel. So on the English side we have Dover, on the Belgian side we have Calais.
Okay.
And Dover refers to dove, to that bird.
Okay.
And it probably refers as a profession to somebody who took care of the bird in Holland.
Wow.
So that part of the family also lived along the border. And I have a postcard of somebody who, of an altar that was carved by somebody with that name in the 1500s.
Wow.
It was a shady character.
I noticed how he looked at me when he said shady. Shady like you.
No, I mean the languages, they go freely from one into the other.
History lesson. You should teach
Yeah, in
him.
particular, you are so
Math
far away,
history.
I mean, you don't even know the geography of Europe.
Yeah.
Nope.
So,
Let alone in the U.S.
Nope.
Could ask us like basic geography questions. I guarantee we get them wrong.
Are you born and raised here?
Cause Roger that, boo.
Oh, okay. Yeah, me too. My geography is terrible.
Yeah.
if I remember asking somebody, so what's the highest mountain in the world?
It's the Everest.
It was Mount McKinley.
Not.
Everest?
Not.
And it's still, I mean, it's Mount Everest.
Yeah. I think
Possibly K2 if you want.
I think the real highest thing, like if you measure from like below sea level, whatever, is
Mauna Kea?
yeah,
Yeah. No, but
You know what the tallest waterfall is?
tallest waterfall. What?
Like lengthwise?
What?
Angel Falls.
On Big Island.
no.
Well, I was gonna say wait, that's a Cockle Falls.
What
Huh?
Ithaca?
It's Angel Falls, right?
Is that in Ithaca, Greece?
No.
No, not really.
Where the hell is Ithaca?
You said India?
Hey,
Oh.
man.
Am I right?
Oh, I don't know, maybe Angel Falls is for North America, then maybe.
No, I mean, the highest waterfalls, possibly only America, are upstate New York, right?
That's the whatchamacall, Niagara Falls. Then.
Not Niagara.
Where's
I mean,
Niagara?
Niagara Falls is big, but it's not so high.
Oh.
So, if I remember this correctly, there are a few falls around Ithaca, where Cornell University is.
Oh, you're talking about that Ithaca.
Yes. And if I remember right, they claimed that they were the tallest waterfalls.
The world's largest desert.
Sahara?
No.
Snow.
Gobi.
Antarctica.
There you go.
Oh.
Yeah, it was some weird, I remember some weird fact like that. Yeah.
Desert's defined by how much rainfall they get.
Oh, interesting.
0.
Okay.
Where's the deepest hole?
Death Valley.
Huh?
Death Valley.
Death Valley? Oh, that's California, right?
I think he meant it as an analogy.
Oh.
No, I think you meant it. I think he meant it as an analogy.
Or the Dead Sea. I don't know.
What are the interesting facts do you know? That you're gonna fail this class.
Okay, back to math.
Any questions?
Is there a math history class?
Yeah, he used to
there
teach
is.
it.
Oh.
Are you teaching it next semester or no?
But
Math, history of mathematics or whatever. I think, well, maybe that
I
one.
teach 421.
That's the topology one, yeah?
And calculus 4.
Did you have more?
Yeah.
Probably just a donut to the cup thing.
Suppose
Okay.
A subset B
I just thought it
is
was
a
just a
bounded
subset.
set. So A has at most one least upper bound.
Oh, I thought we talked about this.
Yes. Least upper bound. So if we have two, each of them has to be smaller or equal to the other one, right?
Oh, you're asking which, the least upper
They
one?
have to be the same.
Okay, that one.
Oh, yeah, didn't we break that
That
one
was the anti-symmetry of
Can I read also?
construction.
What was the question?
Suppose A is a subset of S, is a bounded subset. Show that A has at most one least upper bound.
Hey, can't you only have one? Because it's bounded? Like if you have another
Oh,
upper
yeah,
bound?
lots of bounds,
Yeah,
but
but
only one
least, yeah.
So you assume that there's two.
Yep.
You just show that.
Right, so
By contradiction.
by definition, each is smaller or equal to the other.
Yeah.
So you assume.
And by anti-symmetry, they are the same.
Same. Yeah.
Okay.
You want to do that?
Yeah, I think we said, we said, assume to the contrary that this is least upper bound.
When you remember that one lecture where I explained that the real numbers are kind of unique,
Right.
that there's only one model we talked for a little while about these upper bounds, because you use them in the construction of any isomorphism.
What's an isomorphism?
What is
Change.
Shape.
Polymorphism, yeah, morphism is shape, poly many.
so isomorphism
One.
means the same shape.
Same shape. Good job.
So those X-Men that morph from one to another one, they always shapeshifters, right?
Yes.
So, but that's where the word morph comes from, right? Or shape. So isomorphism is they have the same shape.
And you're just referring to two spaces, right?
Well, it depends on what structure you have. Okay, so if you took groups where you just have one operation, then this structure should be preserved. If you have a ring where you have two operations, then both of them are supposed to be preserved. And you can think of many, if you have a topological space, Okay, topological space is kind of described by its open sets. You would like to have a map that, or bijective map that sends open sets to open sets. So it's always a question of what your axioms are, what object you're talking about. So whatever you have is supposed to be preserved.
Okay.
And if you take this in the language of functions, you would say you would like to have a map each way that preserves the structure. And maybe you say, well, I want a structure preserving map so that the composition is the identity. And then you can go further and say, well, I want a relation so that the composition is then you have to build into the relation the fact that it preserves the structure. Relations are actually a good notion. Okay, next question.
I think you keep asking questions. I like yours, the ones you selected. I think you keep asking your questions. I like the ones you picked out.
Okay. So,
My hand is sore.
Should I do it? What's on the goal?
No, it's from
Mine is camera.
That's one that's from fingernails all messed up too. Cut my fingernail too.
Problem 6.
Problem 6.
What time is
A
it?
and B be integers,
238.
and B all go on.
What? I wonder if my cut is infected. That's why it's bubbled up like that.
Was it from swimming?
No, it's from working. I got a cut in the suit and the seat.
Eee. Should put alcohol. Alright.
Soap. I didn't
Not
even
bad.
shower tonight. I got home at like fucking midnight. I went straight to sleep.
If it starts turning funky
You
colors.
want gloves? Yeah, I should, yeah. I didn't think about that at the time. I got strong fingers too, but yeah, we were screwing in some nuts to the thing inside it. So the other guy, I think he's kind of weak, that's why, but they were screwing stuff in. Every time I'd screw something in my hand, I'm like, hold tight. I always had to use the hex wrench and stuff.
Good forearms. Got some strong forearms.
Bingo. Stop. Oh.
What kind of workouts you do? Wrist curls, right? Whatever.
The point here is to show that the least common multiple divides any common multiple. probably you would like to show the other thing, that the greatest common divisor is divisible by any common divisor.
Okay.
So if you have a common divisor, it divides the greatest common divisor. I mean, to get this duality, in particular, part of it, you know that, so at some point, you show that A times B is the greatest common divisor of A and B times the least common multiple of A and B. Yes.
Yes.
So if you show that any common divisor divides the greatest common divisor, that's the same as showing that the least common multiple divides any common multiple. Okay, so dividing here means multiple over here, because together they are the product. So first of all, and I mean, we haven't developed anything for multiples, that's why I was going back to common divisors. I'd like to show that the any common divisor divides the greatest common divisor. So you would like to show that C divides A and C divides B. This implies that C divides the greatest common divisor. So the greatest common divisor is of the form MA plus NB, right?
Linear combination.
We prove that the greatest common divisor is a linear combination like this. If C divides A and B, it will divide this, right?
Mm-hmm. Yeah.
So the fact that we can write the greatest common divisor in this way means that any common divisor divides this one.
Okay.
And it's relevant insofar as it makes a connection between addition and multiplication. Because when we said, what is the greatest common divisor?
Biggest number divided both.
Right, but when you do that, you say, let's say, we look at C. So C divides A and C divides B, right? Two nodes. So this is a subset of the integers. And we have some order relation of it. maybe natural numbers. So you have some order relation. You took the biggest element there, right?
Yeah.
But the other formulation is in terms of divisibility. Can you relate those numbers? One is smaller than another one, and one divides the other one. This is a statement about divisibility. This is not the size of the number. It says C divides this. Okay, you didn't like this order relation on the set of numbers between 1 and 100, right? You remember? That set was partially ordered by divisibility. So one number was smaller than another one if it divided the other one. There are many numbers we couldn't compare and so on. Okay, so the word greatest or divisor, greatest common divisor. We can use greatest in two different ways. One is using an additive idea of the integers or natural numbers. So 7 is bigger than 5. Or you can look at the multiplicative one, where you say 5 divides 10. And the statement here is they are the same. And if you think about the proof of Euclid's theorem, it made essential, or the division algorithm, it makes essential use of both addition and multiplication. Okay, so it's very simple to write down number systems. They're not particularly nice, but we write down number systems where prime factorization is not unique. Besides the ones that we have. Okay? And the point there is you don't have closedness under addition. So if you leave out some, if you destroy addition, then factorization doesn't work anymore. That favorite Math 100 book of mine talks about this kingdom where certain numbers were illegal.
Prime numbers.
No, not the prime numbers, but I think multiples of four or so were illegal. So you could factor some and not others, and then all of a sudden your idea of prime didn't work. Okay, or you don't get uniqueness. So 20 was like 2 times 10.
But not 5 times 4.
And maybe it was 10 was a prime because it didn't allow multiplication with 2 or so. I don't remember the exact details. But the point is, the Euclidean division algorithm makes essential use of the connection between addition and multiplication, including the distributed law. So if you write down the algorithm, the greatest common divisor does not change as you go through the calculation. And this one here means you could have formulated greatest common divisors differently. And you can purely multiplicative. And an abstract algebra, some people may do that.
You said when you use the algorithm, the GCD doesn't change?
When you reduce modulo or something, remember the process.
Yeah, it's like,
When you divide it with remainders,
yeah.
M is plus R.
Yeah.
The greatest common divisor of M and N is the same as the greatest common divisor of N and R. If a number divides N and R, it will divide M.
Sure.
If it divides M and N, it will divide R.
Oh, because you can express M minus
So
2
that's
then.
how you get that these sets have the same divisors.
Okay.
If they have the same divisors, they have the same greatest common divisors. But the point was, it's addition and multiplication.
So what, how many questions on the exam?
No idea.
Anything
Less than 25.
24.
More than 3.
Anything we should study in particular?
Everything.
Okay.
Or
There it is.
It's gonna be a hell of a